By utilizing the Maclaurin series of the highlighted functions, we can derive the Maclaurin series for all other functions. To determine the Maclaurin series for the function 1 over 1 minus x, we calculate its derivatives. By substituting x with minus t squared in the Maclaurin series for 1 over 1 minus x, we obtain this. Integrating this series term by term yields the Maclaurin series for inverse tangent. Using the relation here, we can derive the Maclaurin series for inverse cotangent. By substituting x with minus t in the Maclaurin series for 1 over 1 minus x, we obtain this. Integrating this series term by term yields the Maclaurin series for ln 1 plus x. By substituting x with minus x in the Maclaurin series for ln 1 plus x, we obtain this. Furthermore, using the equality here, we can derive the Maclaurin series for ln 1 plus x over 1 minus x. Here, we use the fact that is stated. Using the equality here, we can derive the Maclaurin series for inverse hyperbolic tangent. To determine the Maclaurin series for the function sine x, we compute its derivatives. Using the identity here and differentiating the Maclaurin series for sine term by term, we can derive the Maclaurin series for cosine x. Any number of terms in the Maclaurin series for tan can be calculated from the Maclaurin series for sine and cosine using the long division algorithm. The exact expression for the coefficients in the Maclaurin series for tan is rather complicated and involves Bernoulli numbers. Using the long division algorithm. Any number of terms in the Maclaurin series for secant can be calculated from the Maclaurin series for cosine using the long division algorithm. The exact expression for the coefficients in the Maclaurin series for secant is rather complicated and involves Euler numbers. Using the long division algorithm. To determine the Maclaurin series for the function e to the power x, we first compute its derivatives. Using the identity here, we can derive the Maclaurin series for hyperbolic sine from the Maclaurin series for e to the power x. Using the identity here and differentiating the Maclaurin series for hyperbolic sine term by term, we can derive the Maclaurin series for hyperbolic cosine. Any number of terms in the Maclaurin series for hyperbolic tangent can be calculated from Maclaurin series for hyperbolic sine and hyperbolic cosine using the long division algorithm. The exact expression for the coefficients in the Maclaurin series for hyperbolic tangent is rather complicated and involves Bernoulli numbers. Using the long division algorithm. Any number of terms in the Maclaurin series for hyperbolic secant can be calculated from the Maclaurin series for hyperbolic cosine using the long division algorithm. The exact expression for the coefficients in the Maclaurin series for hyperbolic secant is rather complicated and involves Euler numbers. Using the long division algorithm. By substituting x with minus t squared in the Maclaurin series for e to the power x, we obtain this. Integrating this series term by term yields the Maclaurin series for the error function. The cumulative distribution function of the standard normal distribution can be expressed in terms of the error function after the change of variables in the integral. This allows us to find the Maclaurin series. Computations. For the standard normal distribution, the mean is mu equals 0, and the standard deviation is sigma equals 1. The probability represents the percentage of the population within A and B standard deviations from the mean. For example, to determine the portion of the population that is one standard deviation above the mean, we set A equals 0 and B equals 1. On the following slide, we will observe approximations of this result using partial sums of the series for increasing values of n. Partial sums of the series for increasing values of n. To determine the Maclaurin series for the binomial series, we calculate its derivatives. Let alpha equal minus half. By substituting x with minus t squared in the Maclaurin series, we obtain this. Integrating this series term by term yields the Maclaurin series for inverse sine of x. Let us prove the equality here. Using the relation here, we can derive the Maclaurin series for inverse cosine. Let alpha equal minus half. By substituting x with t squared in the Maclaurin series, we obtain this. Integrating this series term by term yields the Maclaurin series for inverse hyperbolic sine. The coefficients of the Maclaurin series for the inverse sine are positive. The coefficients of the Maclaurin series for the inverse cosine are negative for n greater than or equal to 1. The coefficients of the Maclaurin series for the inverse sine are positive. The coefficients of the Maclaurin series for the inverse hyperbolic sine are alternating. Generalized hypergeometric functions are defined via series expansions, where this is the Pochhammer symbol. This is the exponential function. It solves the differential equation here. This is the confluent hypergeometric function. It solves the differential equation here. This is the binomial series. It solves the differential equation here. For a equals 1, we get the geometric series with a ratio x and a coefficient 1. This is the confluent hypergeometric function. It solves the differential equation here. This is the Gaussian hypergeometric function. It solves the differential equation here. The general term of this series is this. Maclaurin series based on geometric series can be expressed in terms of Gaussian hypergeometric function. In the subsequent slides, observe that if a is a non-zero real number, then this. In particular, we have the following. Additionally, note that if k is a positive integer, then this. In particular, the following. 1 over 1 minus x. Inverse tangent. Inverse cotangent. Logarithm 1 plus x. Logarithm 1 plus x over 1 minus x. Inverse hyperbolic tangent. Non-zero coefficients of Maclaurin series for functions that are odd, like sine and hyperbolic sine, or even, like cosine and hyperbolic cosine, correspond to odd or even powers of x. The coefficients of Maclaurin series for the trigonometric functions sine and cosine, or hyperbolic functions hyperbolic sine and hyperbolic cosine, are alternating or positive. We can also derive the Maclaurin series for the functions sine, cosine, hyperbolic cosine, using the Maclaurin series for the exponential function using the representations here. For the hypergeometric functions on the subsequent slides, we shall use the following identities: sine, cosine, hyperbolic sine, hyperbolic cosine. Non-zero coefficients of the Maclaurin series for functions that are odd, like tangent and hyperbolic tangent, or even, like secant and hyperbolic secant, correspond to odd or even powers of x. The coefficients of the Maclaurin series for trigonometric functions tangent and secant, or hyperbolic functions hyperbolic tangent and hyperbolic secant, are positive or alternating. The exact expressions for the coefficients in the Maclaurin series for these functions are rather complicated and involve Bernoulli and Euler numbers. Additionally, these functions are related to hypergeometric functions in a complicated way. Using the identity here, we obtain error function. Consequently, it follows that this, in Wolfram alpha, this would be the following. Using the identity here, we observe that this, additionally, will call this. 1 plus x to the power a inverse sine inverse cosine inverse hyperbolic sine. Thanks for watching.